To the Observatory of Capodimonte, and welcome to Naples. I'm standing here on behalf of the Capodimonte Observatory personnel, and in particular on behalf of the local organizing committee, which includes also colleagues of the Department of Physics at the University of Naples, to wish you a pleasant conference. The idea of this conference came up in the main discussion we had with Massimo Capaccioli about the project that we are carrying out in Naples, and the ones that we have been collaborating over years outside Naples. So the idea of the conference was modest, I have to say. We wanted to gather outstanding experts of dark matter on all scales, from ghost galaxies to cluster of galaxies and beyond, and dark energy specialists, theoreticians, and experts on simulation, and finally people working on extended gravity to make the status of the research in the dark sector of the universe. So honestly, when I started all this, I didn't think we really could make it, because it was in fact a little bit ambitious. So when I started touch base with most of my estimated colleagues who became then part of the scientific organizing committee later, I did not expect so much enthusiasm. The more I kept contacting people, the more I received positive reactions and useful suggestions. It was like a wave growing, which made us to assemble at the end an exceptional scientific committee. And I've seen also books of a Galaxy Dynamics book ready to be autographed around. A great list of invited speakers, a very interesting program, and finally a wonderful audience. I first deeply thank all of you for coming. You made us, me, the SOC and the LOC, very proud of the work we've done. But I have to thank, of course, the SOC first, because it made a very great job, and the LOC that made all these things possible. I also have to thank the National Institute for Astrophysics, INAF, for their support, the Department of Physics of the University of Naples, and the Italian Society of Gravity that have contributed to this organization. I have to finally thank the people who are making this workshop a little more special, having been in charge of the organization of the live streaming and live chat, to broadcast the workshop well beyond the walls of this auditorium. The students of the Science Journalism Project and the team of the Public Outreach Capodimonte. It's the first time that students will produce a multimedia coverage of the conference, and we hope this will be a format for future projects. Finally, a sad note, sorry. This conference came after the loss of a great scientist and a great woman, Vera Rubin, who left us last year. So it was an idea of Massimo Capaccioli to entitle this conference to her, and Magda Arnaboldi, who's here, will going to say a few words in her memory.
First of all, thank you, Nicola, for all your hard work and for bringing all us back to this beautiful place. I'm linked to the Observatory of Capodimonte because I've worked here for 4 years more. And it's always a pleasure to be back. I will be the chair of the first morning session, and through the email exchange with Massimo and Nicola, we felt that a short speech, a short commemoration was in order. We are here probably because of the intuition of this very gifted astronomer, Vera Rubin. Many things have been said about her, and I'm going to be short. I want to, first of all, illustrate these two pictures, which I thought, which I thought it was great. First of all, because in the first one, in 1965, you see a young person, highly motivated, interested, working at the telescope. And you can see really the energy and the passion for what she's doing. And as a parabola trajectory in life, you see on the other side a person that is a reference for all of us, that through this career has actually made a dream come true. And I think this is really fantastic. And regardless of the age of our experience, the real passion of astronomy can really bring us together. Now, I'm an Italian, I'm an astronomer. I have met Vera Rubin a couple of times in person, and I started during my astrophysics graduation by studying her papers, and it was actually quite exciting during my life when she was actually a referee of my paper, and she said that she enjoyed reading my thoughts, my ideas, and there was a link through different astronomers, different countries, different education, but through this passion that we share, we can really reach for each other and share in the learning of the universe. Thank you, Vera Rubin.
Thanks, Magda. This is a nice memory. And so I think this is the time to start. So we really hope that you will enjoy the meeting and try to be more interactive as possible, to take your chance and every moment during the conference to talk to each other, because we're expecting this to be a very exciting conference. Okay. Enjoy.
Very good. I'm now your chair for the morning session. And the first speaker is James Bullock. The title of his contribution is Astrophysical Constraints on the Nature of Dark Matter. And James, you should be here.
Okay. Thank you. Thanks, everyone. This is it's a great pleasure to be here, and definitely excited for the meeting. So I wanted to talk a bit about trying to use astrophysics to constrain the nature of dark matter. Before I begin, I want to just mention stuff I'm going to talk about involve a whole bunch of people. I listed their names here, including several graduate students at UC Irvine, including Oliver Elbert and Andrew Grouse, some postdoctoral researchers there as well, Alejandro Gonzalez San Diego, Victor Robles, and then a number of people who are at other institutions who we've been collaborating with as well. So the context of this talk is that we have this standard model, LCDM, that I'm sure we'll hear a lot about today. And this model is quite excellent. It does a very good job of explaining especially the large-scale universe. But I want to talk about the possibility that this model is just a simplified version of what really sits beneath. And specifically, I'm going to talk about the dark matter wedge. Before I do that, I want to just maybe explain one way that I'm thinking about this problem by focusing on the normal piece. So as we all know, about 5% of the clustering, of the energy density of the universe is in the form of normal stuff, the baryons. We also know that this normal stuff is pretty complex. All of the standard model of particle physics is included in there, and then all of the vast complexities that can arise with the physics of this 5% wedge. In the context of our standard model here, this 25% piece, this other giant piece of the universe, is basically one particle that doesn't really do anything. It's born cold, it's pretty massive, it doesn't interact with normal matter very much at all, and it doesn't interact with itself very much at all. So this is the simplified picture that we have, and so we might ask ourselves, is this necessarily so? So there are a lot of ideas these days that come to us from the particle physics community that the dark matter is not quite so simple. That it's possible that there's a whole smorgasbord of particles and interactions sitting in the dark sector that are doing interesting things. There's ideas for dark photons and dark atoms, and we'll hear more about these kind of models probably from Mark, who'll talk right after me, and maybe other speakers this week. So just thinking about this, for me, the question is, what can astrophysics say? Can astrophysics bring anything to bear to constraining these possibilities? So, you can ask yourself, what's my agenda? Broadly speaking, my agenda is I'd like to sort of ask, what can astrophysics tell us about the nature of dark matter? Is it cold, is it warm, or is it ultralight and some kind of wavy kind of dark matter? Those are possibilities that are explored. is there, in fact, a dark sector where these complicated interactions perhaps are happening? Or is it all an illusion in that, in fact, we really just don't understand gravity, and we'll hear more about that later. Motivating this, perhaps, are some puzzles with the cold dark matter paradigm, and I'll talk a bit about some of those today, including this cusp core problem, the too big to fail problem, and then something else which I sort of want to talk about is the diversity of galaxy rotation curves in the face of the regularity we also see in the scaling relations between baryons and dark matter. And finally, I'll talk about, at the end, I want to talk a bit about finding dark substructures, and specifically refining our predictions or our expectations for the nature of those dark subhalos, because I think if we can find truly dark subhalos, this will be an amazing achievement and really sort of confirm that this model, this sort of lambda CDM model, at least a cold dark matter type model, is pretty close to right. We all know that the lambda cold dark matter model works really well on large scales. This is a picture that demonstrates that. And so what I want to do is focus on sort of small scales, specifically, below about a mass scales of about a Milky Way. We're going to hear a little bit more later, I think, about the Lyman alpha forest and trying to constrain, for example, warm dark matter with that. I'm going to focus mostly on nonlinear stuff on these scales, trying to use nonlinear predictions to constrain these models. So let's start. Imagine you have a lambda cold dark matter simulation and you pick out a small spiral galaxy, or at least the kind of halo that we think might host a small spiral galaxy, and you simulate it with very high force and mass resolution. What does it look like? Well, one thing you can see here is it's filled with substructure of its own, but the simplest thing you can do is measure the density profile, and it's well known that these kind of profiles, at least in dark matter only simulations, are very cuspy. They look like an NFW or an inosto profile, and they produce rotation curves that rise very quickly with radius. There are a number of galaxies in the universe, perhaps most galaxies in the universe. If you look at their rotation curves, they seem to prefer core-like density profiles and not these cusps. So this is the old cusp core problem that's been around a very long time. It's still there, and it's still not clear whether we can solve it, I think, with baryon physics, which I'll return to in a bit. There's another thing. This is an issue that's been around for a while as well, but it was nicely sort of discussed in this paper by Oman et al. Associated with diversity. So we see here sort of the expectation for the kind of rotation curve you might naively expect in a certain class of hydro simulations without really strong explosive feedback in green, and then a number of rotation curves of galaxies that have about the same maximum circular velocity shown here with the data points. And what you can see is that there's a huge variety, especially in the central mass densities of these galaxies, compared to what you would naively expect. So the subtext of this paper, I think, was actually just that there's something wrong with the data. But I'm going to put that idea to the side for a second and say if we take the data seriously, there is this diversity issue. Now what Oman et al. Did is they developed this way of characterizing the diversity, which is here reproduced by a figure made by Peter Treacy, where you take, say, a radius, say here at 2 kiloparsecs, and you measure the circular velocity there, and then you plot that versus sort of the flat rotation curve, which is plotted here. And you get these points. So each one of these points is a galaxy rotation curve. And the large amount of scatter here in the vertical direction is supposed to be this diversity. The naive expectation for what that diversity would be in a CDM model is shown in this shaded black band there, and you see it just looks strange. There's a huge amount of scatter. And a one-to-one line would just mean you hit Vmax at 2 kiloparsecs. So that's why it bangs up there. This is particularly interesting to me if you compare that observed diversity versus other observed regularity. So we've seen this with the baryonic Tully-Fisher relation, but another way of sort of generalizing baryonic Tully-Fisher was shown in this paper that Stacy had a few months ago, I guess, or weeks ago, I don't even know. I can't remember anything. This is the acceleration of baryons. You would expect v squared over r, the radial acceleration for baryons, versus the observed acceleration that you get totally in a rotation curve. And galaxies tend to obey this rather tight relationship between the observed rotation, between the observed acceleration that you measure directly from the rotation curve, and what you would naively expect from the baryons. So this is very interesting, and it's very tight. Up here is where things are baryon dominated, and down here is either the flat part of the rotation curve or the inner parts of very dark matter dominated low mass galaxies. And given this amount of diversity in galaxy rotation curves, it's very interesting that they suddenly become regular again when you plot them versus the baryonic content. And trying to understand why this should be is, I think, an interesting puzzle. Because where the baryons get small is naively where you think feedback's not going to matter that much. But, so anyway, so for me, while there have been a lot of papers sort of addressing this relationship in the context of CDM, at least to my mind, no one has really tackled this issue, which I think is the puzzle, at least for me. I might be wrong about that, but in my reading of these papers, I haven't really seen it discussed in that way. There's another problem that's been lingering for a long time, missing satellites, and that's the prediction that halos like the Milky Way should be surrounded by lots and lots of dark clumps, and we only see a few tens of satellites now. We think there's about 50 dark matter dominated or dwarf galaxies around the Milky Way, but we predict thousands, so it's still kind of, the numbers don't match. In many ways, though, the missing satellites problem is just sort of a extreme version of the fact that the observed stellar mass function of galaxies has a Feynman slope that's very flat compared to the dark matter mass function, which is very steep. So the expected dark matter mass function is shown here in the black line, and then the observed stellar mass function is shown by these stars. And the point being that the dark matter mass function should keep rising very steeply, the stellar mass function is flat. One way to parameterize your ignorance there, this has become very common as you adopt abundance matching, which says we can map halos and galaxies in a one-to-one way, assuming the biggest galaxies sit in the biggest halos, and that allows you to derive relationships like this between the stellar mass of a galaxy and the halo mass of a galaxy. You could just ask, well, if I apply this relationship and extrapolate it down to the stellar masses where we observe satellite galaxies, can you solve the missing satellites problem? Do you get the right counts? And the answer is that you do. So the answer is if you just take stellar mass halo mass relationship, extrapolate it down to the stellar masses of dwarf satellites around the Milky Way, you can explain the counts pretty well. So in that sense, it's not that surprising. You can solve the problem. Now, whether you understand the feedback that you need in order to make this happen is unknown, but in that sense, they're similar problems. It's sort of one and the same problem. So we have this picture in mind then that you have the biggest satellites are being hosted by the biggest halos. And that seems natural. And when you do that, you get the counts right and everyone's happy. The problem is if you go in and you measure the masses of these satellites and compare them to the masses of the dark matter halos they're supposed to be sitting in, they don't match. So this is the essence of the too big to fail problem. So if you plot the rotation curves of all these big things, here in pink, and you measure the masses at the half-light radii of these galaxies, the densities are all much below what you would naively expect them to have if they were sitting in those massive halos. If you go beyond the virial radius of the Milky Way, you see this same problem. So if you go outside the virial radius, but still within the local group, and you look at local group galaxies, and you count how many subhalos there should be, and how many halos there should be, plot the rotation curves, compare them to the observed galaxies. Again, the predicted ones are denser than the observed ones. So in some sense, this is reminiscent of the cusp-core problem, in that things are denser than they should be. But it doesn't rely on measuring slopes. It's just sort of an absolute measure of mass, and things just appear to be too dense in the theory compared to what's observed. We also see this in the field. So this is a paper by Papastirgis that came out not too long ago, a few months ago. Now actually comparing to, I think these are rotation curves from the Nihao simulation predictions, if I remember correctly. Is that right? And even here, and so therefore these are simulations with feedback. I'll talk about that in a second. These are simulations with feedback that actually produce core-like density profiles in the middle. But still, there's this issue. And the main issue is that the density measurements appear to be too low at very large radius. So typically you can reduce the central densities within the radii where the stars are because you're getting it from feedback. But if you have a rotation curve from H1 that goes well beyond where the stars are, you still see this too low value. So the question is, can you solve these problems with feedback? If not, what do you have to do with dark matter? And do the models, and then to turn the question of dark matter on its head, what are the limits on these different kind of dark matter models? So this is just a simulation from our group. This is done using fire simulations led by Jose and Yorbe. This is just one example of a dwarf-sized thing, this kind of halo that would be sort of a too-big-to-fail halo that you want to lower its densities. What's plotted in black is what you get if you run the dark matter-only simulation, and what's plotted in red is the density profile of the dark matter in the baryonic simulation. So you see it bopping around, and what's happening, there'll be a starburst. In response to that starburst, gas is ejected. That creates a sort of shock to the potential, and that makes the dark matter profile go down. But this halo continues to grow with time, so there's dark mergers that refill that loss cone, and it grows back to where it was. Eventually, after a while, things settle down, and you can produce a pretty significant core just from feedback. What we found with a series of simulations sort of targeted at this crucial mass scale of sort of too big to fail, what we found is that we can create pretty big cores and lower the densities fairly substantially as long as you form more than about 3 massive stars. No depending on the way the halo forms, but roughly that's what we're finding. And if you form lower than, certainly less than 1 million solar masses of stars, you pretty much don't do anything to the dark matter profile. And I think just like with the Nihal simulations, the size of our feedback cores are about the size of the stellar radius. So we're not producing with feedback significant depressions in the density at radii well beyond the sort of half-light radius of the stars. This is a larger paper. This is Tollett et al., where they've done a similar exercise following along, again, with other work that I've referenced down here. They've basically shown, using a nice set of simulations, that you get a peak in core creation, which is sort of measured along this vertical axis. A higher value is more core-like. You get a peak in core creation in these simulations masses, to halo masses to the mass 3. And down here at low masses, that's when you don't do it. So if you have fewer, again, stars like anybody, if you have more than that, you can start changing things with stellar feedback. So this is nice, it's fairly predictive. A lot of groups, I think, are finding an answer like this. Not every single group, but a lot of groups are finding answers like this. So I think, if you want to think about a place to kind of go after testing this expectation, you want to look at things smaller than about 1 million solar masses. It's at that scale where it becomes difficult for feedback to produce cores and lower densities. So can we understand why low stellar mass galaxies seem to have low dark matter content? This might be a motivation to explore other types of dark matter. Shown here is a Milky Way-sized halo simulated with cold dark matter, self-interacting dark matter, and warm dark matter. Let me start with warm dark matter. Qualitatively, on nonlinear scales, what does warm dark matter do? So it reduces substructure. It gets rid of small halos for you. That's kind of what it does by cutting off the power spectrum. It also makes the small halos that do exist less dense. It doesn't make them core-like on its own, but it does lower the densities because things form later. And in fact, there are viable models of warm dark matter that can both lower densities enough to help alleviate the too big to fail problem and produce enough satellite galaxies that they're not already ruled out by the 50 that we see. But it's actually getting very close. If we're getting to the point where we find it, if we know for sure there were 100 satellites, which there probably are, but if we knew for sure there were, it would get very tight for models like this, I think, to both alleviate too big to fail and not have too few satellites. Interestingly enough, though, this 3.5 keV line is not going away. There was a paper today on the archive that I just threw up here. And the models that are starred here that we ran a little while ago would sit here in this diagram of sine squared 2 theta versus the sterile neutrino mass that would reproduce this kind of line. So the new Chandra deep point is right here. And this star is sort of in between these two models here that are both consistent with the data. So if this is real, it's still possible that we would have to take into account. It would change structural formation a little bit. It would alleviate too big to fail, but we still have enough scale. So maybe this is true. Note that the Hitomi 3 sigma constraint is up here, so it doesn't exclude this. So, take this for what you will. People argue back and forth about whether this is real. I actually looked at the plot. I wasn't didn't really look like 3.5 sigma to me, but I'm not an expert on this. So anyway, it's interesting to think about. The other thing I want to talk about is self-interacting dark matter. I think Mark will talk about this too. The way that we have been approaching self-interacting dark matter is to think about it separately from the power spectrum. There are self-interacting dark matter models that will reduce power on small scales, kind of like warm dark matter. But there are other models that don't, and they produce things on small scales that look like CDM in the power spectrum. But the self-interactions themselves do interesting things to the structure of halos. So the way you parameterize this is with sigma over m, 1 centimeter squared per gram, is the cross-section of relevance to give you interesting effects. So SIDM like this actually produces subhalos. The subhalo distributions look pretty much identical to CDM. So it doesn't change the subhalo counts. What it does is it makes cores in the central regions of galaxies. You can try to place constraints with cluster mergers. They're not very strong. But another thing you can do is just measure the central densities of clusters. And it turns out that the central densities of clusters by themselves rule out cross-sections smaller than about 0.2 centimeters squared per gram. So the central densities of clusters actually are a little lower than you would expect in CDM. Here's one in black line is CDM, and the shaded band is sort of constraints for Newman et al. For this particular cluster. See, it's underdense. But a dark matter, SIDM model with 0.1 centimeters squared per gram actually produces central densities that look pretty good in a model like this. But if you crank up the cross-section too high, you actually undershoot the densities. You don't dense enough. And so what this means is on the velocity scales of clusters, we need cross-sections lower than about 0.2 centimeters squared per gram. That's not quite high enough to solve too big to fail and these other problems on small scales. So what you would need to resort to is a model that has a velocity-dependent cross-section, which isn't necessarily crazy, but these are the kind of models that you kind of have to go to if you want to sort of both match cluster constraints and also solve small-scale problems. But if you go to something like 1 centimeter squared per gram on the scale of dwarfs, you can indeed do that. Okay. So one of the other interesting things you get in these SIDM models is you get a lot of crosstalk between what the baryons and the dark matter are doing. When you take that into account, you actually can explain this diversity problem that I talked about earlier. So because there's crosstalk between what the baryons are doing and what SIDM is doing, if you have low baryonic content, you can have low core densities. If you have slightly higher baryonic content, you get a lot of contraction in SIDM, more than you do in CDM, and that creates a tremendous amount of scatter in these diagrams. So I think SIDM actually can help you explain the diversity in galaxy rotation curves on those scales. And we're trying to figure this out, but I also think it could, in principle, help understand the tight scaling relations as well because of this crosstalk between baryons and dark matter and SIDM. Finally, I'll just say we're running SIDM models with full hydro now. Those models are, what's interesting is SIDM appears to be fireproof in the sense that the predictions are very robust on the scale of dwarf galaxies, even when you have very strong feedback. So things are actually quite robust there. And so you get cores, for example, in ultra-faint galaxies, etc. So this is a way of testing these models. So very quickly, I'll just end. I know I'm over because I'm a bad person. Yeah, I'm getting scared now. I'm almost done. So one thing I just wanted to say, I mentioned earlier that I think substructure is a really big deal. I think we should try at all costs to find this dark substructure, and we have talks later in the week looking for this with gravitational lensing and with stream heating. One of the things we have to take into account is that if you're comparing your predictions to dark matter only simulations, you're comparing your observations to dark matter only simulations, those are not the right things to compare to. In the central regions of galaxies, okay, this is a pure in-body simulation. This is if you run the same simulation with full hydro. You wipe that stuff out like crazy. And this is coming just from the existence of that galaxy to the baryon potential. It's not coming from feedback. It's just if you have a galaxy in the center of your halo, it rips stuff apart. And all those subhalos go away. So there's many fewer subhalos out there to look for than you thought, unfortunately. So finding this, the predictions need to take all this stuff into account. So I'm going to leave my conclusions there since I'm way over, and thanks for your patience.
Thank you, James, for this very interesting talk. Now, I ask the audience to be disciplined. So please ask your question by speaking on the microphone. So over there.
You said that self-interacting dark matter only changes something in the core, but does not change the count of substructure. So how do you make this statement? Since Maxwell, we know that every interaction between particles assumes there is some other particles that mediate this interaction. So you have to specify. When you say self-interacting, it's not one model. It's a very, very wide class of models. So you have to tell what's going on in the early universe, and then we will know what is the primordial properties, and then we can say whether it changes something for substructures.
I should have clarified that. So what I was trying, and I tried to say this quickly, but I didn't do a very good job of it. If all you put into your simulation is the existence of the self-interaction itself, so the scattering probability between two dark matter particles, that in and of itself does not eliminate substructure. But it's very reasonable to expect that if you try to build a model from first principles that does have these interactions, there could very well be things going on that would stream out, that would flatten out fluctuations on small scales and create a power spectrum that looks more like warm dark matter. But the physics of what would create the suppression and substructure in that sense is just the power spectrum and not the actual interactions themselves in late times. That's all I meant. And I think Mark will talk about models of those kind, which you might argue are sort of realistically motivated, that sort of do both at once. Yeah.
Okay.
Yeah, so going back to the first point that you made, that we are trying to fit all this with one particle or one dominant particle. I was wondering, isn't it perhaps time to consider that dark matter is a mixture of particles? Has anyone tried to do simulations where there is cold and warm at the same time? Would that potentially solve the problem, mitigate it?
So I know that there are some people who have done cold and warm and models like that at the same time. And that, in principle, yes, can help things. You just sort of have a mixture. What tends to happen is the coldest particles wind up in the and so things are still cuspy, but the normalizations are a bit lower for a given sigma A. Another thing people are thinking a lot about are sort of tiered models in SIDM, where you have very strongly, some small fraction of your particles with very, very strong interaction, have very, very strong interactions, and other have small interactions, etc., sort of a whole cascade as well. I'm not aware of anyone who simulated that. I know that I have been bugged a lot by people who want us to do that, and maybe Mark has, maybe you've done some of that, I don't know, multiple SIDM models at the same time. It's interesting to think about. I think my attitude is I'm still trying to kill this one, and we still can't kill this one, but I think in principle, all kinds of things can be going on, and I think when we do this, this is just a toy model. I think it would be weird if the universe actually had sort of completely elastic, spherically symmetric scattering like this. But I think of this as sort of a toy model, and let's see if we can rule it out and what kind of intuition we can gain. But it's very possible there's a whole cascade of particles that are doing all kinds of things.
Okay, we can have time for one quick question. Oh, good. Yeah, that's good. Andrea,
Please.
go ahead.
I need one
Speak on the microphone, please.
Do you want me to put a plot?
I need one of James' plots, it's fine.
Yeah, no, I can do it. Which one?
I was intrigued. That is due to the fact that in one plot there were 4 orders of magnitude on the y-axis, in the other one there was almost 1 order of magnitude.
Yeah, I mean,
so
you know.
I think naively the scatter is not that different.
Okay.
I was wondering whether
I mean, that's a good point. I mean, it's very possible that, you know, according to, although, you know, Stacy says that the scatter on this one is consistent with just observational errors, right?
What about the other plot? Is it?
Yes,
I mean, it seems that you're not putting them on the same ground.
You're right. It's unfair. The axes differences are very big. I'm just trying to, you know, I kind of wanted to get your attention, so it worked. But
Definitely.
There's a simple answer to your question.
Wait for the microphone, please.
Okay, so there's a simple answer to this, and that the scatter on the right is real. So what they're doing on the right is measuring the velocity at a particular physical scale. The plot on the left is more or less reproduced if you plot everything as a function of optical scale length. Okay, so the diversity, if you measure it in kpc, is real. It goes away if you scale by the size of the